All right, and welcome back, everybody. So, last time we finished up our second unit by talking about the center manifold theorem. And yeah, it got a little tricky, a little technical in places, and that's because it has to be. And we are now getting into the part of the course where there is a fair bit of nitpicking in the details to make sure that we can define something appropriately, or that we can really explain a phenomenon or a certain type of dynamics appropriately. So, as we go into the next unit, right, the final unit for the class is a unit on an introduction to chaos. Now, chaos theory in particular is a still kind of a budding field, so to speak. There is not a whole lot that is very well understood about chaos, right? So what we have to do for now is, if we're going to talk about chaos theory, we really need to hash out what it is, and there's still a lot of debate as to what exactly constitutes the definition of chaotic dynamics. So it's actually, I think, better to start off this introductory unit on kind of making clear why this is so difficult to define. So here's what we're going to do for the first video. We are going to figure out what is definitely not chaos. Okay? And if we're going to define this, we're going to figure out what chaotic dynamics cannot be. Then we're going to be better equipped to figure out how to define it specifically. So, if we can't define it specifically, maybe let's just figure out what would we like our qualitative definition to be for what chaos should mean. And we've seen a couple examples here where we want to fit chaos to a colloquial definition. And we've seen that to mean that chaos should be a wandering, deterministic system whose long-term behavior is practically unpredictable. Right? From a theoretical standpoint, any one of these deterministic systems has behavior that is defined, that is perfectly known into the future. The problem is putting that into practice and trying to figure out how to use this in a practical setting. And it turns out that this is very difficult for us to do in a practical setting. And, well, we're going to have to find a way to measure that. Like, why is this so hard to measure long-term behavior of a system that is deterministic? Well, let's start diving into an answer. Let's see if we can't start developing what we need to understand, or figure out what we need to understand more succinctly, more concisely. So, to see how careful we have to be with our construction of chaos, we're going to go through an example of something that is very close to chaotic behavior, but is not quite there. And it's a kind of dynamics that we haven't really discussed yet. So it's worth diving in and making sure we make the distinction between what the dynamics we've seen so far is and what we would like to make sure chaos resembles. So the following example is going to take up the rest of the page, so make room in your notebook. This is a long example. And all that this example is going to be, as simple as it sounds, is essentially a pair of hanging mass spring systems. Now, these are going to be two systems that are decoupled, but we are going to kind of see how they behave relative to one another. So instead of maybe a mass spring system where you have different masses on the end of the springs, like it's the same spring but maybe a different mass, so you could think about this setup as those mass spring systems, or think about it in terms of, as silly as it sounds, maybe you're sitting at a red light and you're trying to match up your turn signal with the car in front of you, and you're wondering, okay, it's going to happen now. Oh shoot, we didn't sync up, or we got really close, or it's going to be really hard to get your turn signals to line up properly. This example, in some sense, is going to answer why that's the case. But the point is that we're going to start with this... oh, shoot. Come on now. Work with me. There we go. We're going to start off with this second-order system of decoupled ODEs. And the first thing that we do is we understand, okay, yeah, we can totally solve these systems independently. Yeah, so we can figure this out. Like, this is not a hard problem to solve in the sense of getting exact solutions. And in fact, we can go so far as to write it as a first order system. And that would put it in 4 dimensions. So our state space would be quadruples, ordered quadruples, x1, y1, x2, y2, living in R4. But the point is that we can just go ahead and solve this guy very quickly and see that we have, probably no surprise here, we have linear combinations of sines and cosines in each of the components, right? And the important guys here, the important variables are x1 and x2, the original displacement variables for the springs. And sure, we can put on some initial conditions and solve for these coefficients a1, b1, a2, b2, but the point is that both of these solutions are sinusoidal, they are periodic, they're bounded, they're very, very predictable. And that's not the point of this exercise. The point of the exercise is to figure out how their dynamics work together and to explain how this pairing of their dynamics is not a chaotic system. So, in order to study this a little bit more concisely, we're going to start reducing the dimensionality. We're going to try to figure out how to, just like in center manifold theory, we're going to try to reduce the complexity of the system that we want to study. And remember, solutions to this system here, right, this 4-dimensional first-order system, right, solutions are still just curves, but the curves now live in R4, right? The phase space is R4 this time, right? So it's a little bit tricky to imagine a curve sitting in R4, but it's not impossible to visualize this. So we would like to figure out a way to reduce the complexity so that we can visualize this a little more simply, or maybe understand the dynamics in a smaller subset of that phase space. And we can see this system is Hamiltonian, right? There is a Hamiltonian that we can assign to the system that creates the same dynamics. And if we go to natural coordinates, right, whatever that might mean, physicists will understand this. The natural coordinates for this system, we're just going to go ahead and distribute the angular frequency onto both the x1 and y, the x and y terms, so it's more even. And when we do this, we can switch into polar coordinates. Why do we want to switch into polar coordinates? Let's find out. So if I did, and this I here is representing either a 1 or a 2, right? So I equals 1 or 2, but fix it for each one of these pairs of equations. If I switch into polar coordinates, then differentiating this, this r squared equation, no surprise, it's going to wind up with a nice little implicit differentiation, a little bit of chain rule. And let's kind of zoom in on that guy first. Let's take a look at the right-hand side of the r squared equation first. After differentiating this guy, we see that I can replace x1 dot with omega 1 y1, and I can replace yi dot with minus omega 1 x1, or whatever I would like to choose. And once we make that substitution, we find that this derivative, this derivative of ri with respect to time, has to be 0, so that we are all actually just staying on circles for this entire process. And that's, again, maybe not so surprising, right? This is simple harmonic motion, and simple harmonic motion lives on ellipses for the most part. So the point is they're on closed orbits in phase space. So great. What about the angle? Okay, so go back to the tangent, right? This theta I equation. And if we differentiate both sides here, we wind up with a tangent squared on the left-hand side, right? And then chain through into the theta I dot. And we have a quotient rule on the right-hand side. Yeah, it's a pain in the butt. However, look at what happens. If I go down a little bit, check this out. This x squared in the bottom, right? This is just like r equals cosine theta from our usual polar coordinate transformation. So we wind up with a nice conglomeration of r i's and cosine theta i's, which we can then use to help us simplify the entire equation here. And we play the same trick with the x dot, sorry, yeah, is that right? With the yi dot and the xi dot in this equation. We use the same guys here, right? Same idea is that we are just replacing those derivatives with what they are supposed to be as defined by the system. And when we do, notice what happens. I wind up with a common omega I term for both of these, and I can factor out the negatives as well. And I'll wind up with an xi squared plus yi squared. And that puts me on ri squared, which cancels exactly with the denominator. And since I was dividing by a cosine theta squared, that's the same thing as a secant squared, which means that my theta dots here are actually constant. So that means that I am on a circle, right? R is constant, so I'm actually on a circle, not just an ellipse. So I'm on a circle, and I'm moving around with constant velocity. All right then. So that means that the radial components here are not terribly important to us. In fact, the dynamics here occur on, well, in each one of these individually, it's going to happen on a circle, and that's a one-dimensional manifold. And I have two of them, kind of at odds with each other, kind of competing with each other. So I really have two one-dimensional manifolds upon which I can define my system, but it's maybe not so easy as saying, oh, I have two one-dimensional manifolds in the phase space. No, they have to work together. So in this case, the dynamics have to occur on this subset of R4. Specifically, both the R1 and R2 variables must be constant, but the theta 1 and theta 2 variables live on a circle, S1. So constants really don't add anything to product sets, so I'm really just working on a copy of two circles working together. And actually, that as a product space is exactly the definition of a two-dimensional torus, right? It's a donut, or at least the glaze, the icing on a donut. Right? We're not talking about the interior, but it's definitely that nice crispy outside, or sorry, the nice golden fluffy outside, maybe with some glaze, some icing on it. But I digress. For any solution to this original system up on top here, the dynamics actually occur on tori. So in other words, R4 is going to be foliated with solutions here, with solution spaces that are, or energy surfaces that are tori. You can actually see them up here as well. It would be H star equals constant, or H equals a constant. So what now? Well, we're going to have to figure out what this torus looks like as it sits in R4. But remember, it's a little bit tricky to see what these spaces look like because they are four-dimensional, right? They do still live in four-dimensional or four-dimensional space, but they are on smaller dimensional subsets. So we need to find some consistent way of visualizing this torus without appealing to what's called an embedding space. So here's the setup that we're going to have. To see why this circle cross circle is a torus, observe that the theta 1 we can think of as telling me about how far around the donut I've gone, how far along the arm of the donut I've gone. And that will be the longitudinal direction. Right, that's what we're going to call the longitudinal direction. And theta 2 here in blue is actually going to measure how we're traveling along a constant theta 1. So if I fix theta 1, there's still a circle cross section that I have here. So that blue one, the blue curve in here, that bounds a disk sitting inside of that torus, that is what we're going to call the meridian, or the meridional direction. So theta 2 has to do with that meridional direction, theta 1 has to do with the longitudinal direction, right? And since we have 2 degrees of freedom here, both of which sit on a circle, we have S1 cross S1 as the defining space, or this is what we call a configuration space, so to speak. So the fixed radii are labeled on that diagram, but you don't have to worry about them for right now because they are both fixed. But we are seeing here that this torus is embedded in 3 dimensions, right? It is a 2-dimensional object. I really want to stress that. There are only 2 degrees of freedom, theta 1 and theta 2. Any point on that torus can be described by a pair, theta 1 comma theta 2. We don't need to know where they live in R3 in order to study what's happening on the torus. Likewise, for our torus up here, it lives in R4, but I only need theta 1 and theta 2 in order to tell you where we are on those energy surfaces. So the point is to come up with a static picture of this torus that is independent of the embedding space, right? Whatever high-dimensional space this torus wants to sit in, our torus is still 2-dimensional. So in order to visualize that guy, we're going to use something called a cell complex. Or in order to figure out a static picture, we'll use a cell complex. And cell complexes have been around since the, since the early 20th century, so early 1900s, when we really started to study algebraic topology more intensely. And that is actually surprisingly, or maybe not so surprisingly, also the work of Henri Poincaré. So a lot of us doing modern topology here, a lot of modern algebraic topology, also falls under his original work, or it's built off of his original ideas. And among these were the idea of a cell complex. And a cell complex is effectively just going to be a disk, or a collection of disks, right? And they don't look like disks because they look like rectangles, but they are topological disks. So what we have in this first picture up top here, this is just that solid square, right? This guy is a filled in square. And what we're going to do is we are going to glue together the left and right edges, and we're going to glue together the top and bottom edges. And we do have to glue them in a particular orientation, lest we come up with things like the Mobius strip, right? We need to worry about orientation. Oh, almost got it. Almost got it. There he is. Okay, so a Mobius strip is what happens when you glue with opposing, or when you switch the orientations on opposite sides. Right, if you switch orientations on both of these guys, you wind up with something called real projective space. If you just do it on one of them, you wind up with a Klein bottle. All of which are non-orientable surfaces. But I digress. We're going to start with that square and then identify the left and right edges and the top and bottom edges with the corresponding orientations. And when we do it one step at a time and see that in the first step, no matter which edges we glue first, we wind up with a cylinder, which is also an annulus if you flatten this guy out, or you stand him up and kind of look down the tube. You see an outer circle and an inner circle spanned by a little band. But either way, if you glue blue first, or if you glue red first, and then you glue the remaining side, you wind up with this torus. So this is going to be our static picture, right? Not the torus down here, but the cell complex up here. We are going to visualize what's happening on the torus, no matter how it's embedded. We're going to visualize that torus as it sits in whatever space by looking at this square and saying that we're going to play a game of Portal as we travel from one side to the other. But we'll kind of play with that picture a little bit more in a moment. Come on, get out of there. Erase. There we go. Cool. So this rectangle is what we're going to take to be our model of this torus. And this is going to be independent of the embedding space. So we actually consider these two to be equivalent, right? The torus is actually a quotient space of that cell complex, or it comes from that cell complex. All right. And now what we would like to do is see how solutions behave on this torus. And we're going to go a little bit further, just a few more minutes here before we kill the video and go into part 2. We're going to check out we're going to see that the solutions are given as constant radius and linear angular velocity. And we're going to go ahead and start out so that theta is going to be 0 to begin with. So we're going to start on we're going to start at the bottom left corner of our cell complex. Right, we're going to be theta 1 equals 0 and theta 2 equals 0 at time 0. So check it out though. We really only care about those theta components because those R1 and R2 are constant. They really don't matter too much in the system. So we're going to, we're going to try to write theta 2 here as a function of theta 1, because this is the natural setting in which the cell complex is constructed. We want to see how theta 1 and theta 2 compete with each other. And through the chain rule once more, we're going to see that the derivative, d theta 2, d theta 1, is exactly what happens when we go through dt. So theta 2 dot divided by theta 1 dot. And we know what both of those are. And it turns out that those, I dropped a negative sign here, but both of those should be negative. And what we wind up with is actually this nice little linear graph. And this is what our solution curve is going to look like as it sits on a torus inside of R4. We're just going to keep wrapping around the torus like so. All right, if I'm going to go ahead and start at this origin at the bottom, what happens when I get to this end here? Well, remember, the right and left sides of the cell complex are identified. So I reappear over here on the far left at the same height, and then continue. And I'll see the same thing where I go off the map on the top and come right back down through the bottom, and then continue on. And this is exactly how we visualize what's happening on the torus, is that we just keep traveling, we keep teleporting from one side of this, the rectangle to the other. And we can continue this ad infinitum. So observe that the sides are kind of like little portals. The sides of the cell complex are kind of portals, and that this black curve, this theta 2 equals omega 2 over theta 1 times over omega 1 times theta 1, is just a line with a slope of omega 2 over omega 1. And we can also visualize this by appealing to the universal covering space, right? You don't have to know what that means. It's just another version of a quotient space, or something that we can get the torus from by making certain gluings or identifications. But we can see exactly why this line is still creating the picture that we see upstairs here. If I zoom out a little bit, notice that this curve corresponds exactly to where we started. And if I go a little higher, let's see, where do we end up? We end up with this guy. We'll go right here. We keep going with that guy and this guy. But the point is that we're kind of keeping the same sort of intuition in mind when we move into different representations of this setup. So what we would like to do here is ask a couple of questions about these lines, about these curves. And well, the question that first comes up is, does this curve ever close up? Does it ever come back to where it started? And actually, it depends. It depends on what that slope is. If it did come back to where it started, though, that would have to mean that it travels, say, p times across the red direction, right? So the red direction here being the longitudinal direction, blue being meridional. So it'd have to be p times across the longitude and q times across the meridian. And it would be for some positive integers, p and q. And then the period would be the smallest relation between these p and q here, or the smallest number of p and q where this would occur. The period would have to satisfy the following two equations here. And I didn't put my tau in the second one. There we go. So omega 2 tau, there it is. Yeah, so that means that I have to cover the same distance, which will be 2 pi times p, and then in the theta 1 direction, and then 2 pi q in the theta 2 direction, and this happens at the same time tau. So if I solve both of these equations for tau and then set the taus to one another, I notice that if this is going to be a periodic solution, right, if the curve closes back up on the torus, then this ratio between, oh, son of a gun, there we go. This ratio between omega 2 and omega 1 has to be a rational number. It's got to be this q over p business. So immediately there's a corollary here that if that ratio is not rational, then the solution curve cannot be periodic. That might be a little bit surprising here, or maybe not surprising, but just to see what this looks like when I have a rational solution, I actually wind up, or a rational slope, I wind up with what are called torus knots as my solutions. Right, and this is a bit of a misnomer since we're working in R4, but it's still a good place to kind of show that on this two-dimensional subspace that I do have something that is knotted inside this, or that I have a trajectory that appears knotted with respect to a three-dimensional observer. And, well, it shouldn't be too hard to see that I'm going p times, so 2 times along the, I have that backwards, I suppose. Anyway, I'm going 2 times in one direction, and p, oh yeah, I do have them backwards. Shame on me, I should actually change that right now. So p and q are reversed. So this is q, p. This is a 3-2 torus knot. There he is. So q is 2 and p is 3. So I should actually be switching these over here. So p is 3 and q is 2. So this is actually a slope. It should be a slope of 2/3 with respect to, no, I have that. No, I feel like I had that right. Anyway, the point is that I have a rational slope between these guys, and I will, at some future time, close up that curve. I will come back to where I started here at the beginning. Now, if that's the case, then we can actually plot what this looks like. And I'm going to use, I believe what I used here is, yeah, this is sine of 3, 2. There we go. So I used sine for both of these. There's no rhyme or reason to why I chose this particular solution to the original system, but I do want to show that if I have a rational ratio between the 3 and the 2 here, which I do, 3/2 is rational, then I actually create this nice closed figure here in plotting the two of these curves together. Notice this is not happening on the cell complex, so don't confuse these figures with the dynamics that are actually occurring on the torus. But this particular figure is something called a Lissajous figure. And Lissajous figures were actually really popular examples in electrical circuitry. When you have an oscilloscope on hand, you can actually see these curves when your components have particular ratios between their resistances or their capacitances. And it actually creates these pretty pictures that you can actually produce from a practical setup. It's not just some mathematical formalism. But that is what happens. This figure closes up when I have a rational slope. But if I have an irrational slope, and I start plotting this, I try to create the same thing. So it's still sine of, let me put this down here. So this is still x equals sine of omega 1t, and then y is sine of omega 2t. And I'm just plotting this for certain time intervals. After 10 pi units in time, I notice that this doesn't actually close up. So maybe I tell myself, I try to convince myself that I just didn't let it run long enough. So I let it run 5 times longer, and I still didn't close up the figure. So maybe I just didn't run it long enough. Where did it close up? So it starts down here, and it actually ends right there. Still didn't close up. Maybe there's some numerical problem in here. Maybe I'm just making an approximation, and that's killing the closure, or maybe I'm not seeing the closure. The problem is that we can actually show that this orbit actually fills the square. So the Lissajous figure fills the square, and the orbit associated with that solution fills the torus in some sense. But how? In what sense?